What if I told you that the two most violently opposed factions in artificial intelligence research, like the massive companies building models like ChatGPT and the rebel academics who are actively trying to replace them, just realized they've actually been building the exact same engine this whole
I
time?
mean, it is the kind of discovery that forces an entire scientific field to just stop, put down their coffee, and completely reevaluate everything they thought they knew about how machines process information.
Yeah, it's huge. Welcome to the deep dive. Today we are unpacking a massive breakthrough in generative AI architecture. Our source text for this is a highly technical, state-of-the-art research paper, and it's titled Transformers are SSMs, Generalized Models, and Efficient Algorithms Through Structured State-Space Duality.
Right, authored by Tri Dow from Princeton and Albert Gu from Carnegie Mellon.
Exactly. And our mission today is to take this dense mathematical Rosetta Stone and, translate it into plain English for you. We're going to explore how this paper takes the two biggest competing AI architectures on the planet, mathematically fuses them together, and creates a vastly faster, smarter foundation for future models.
The implications of what Dow and Gu have proven here are they're staggering. We're talking about a fundamental shift in the actual physics of how artificial intelligence computes language.
And for you listening right now, you might use tools like ChatGPT or Claude or Llama every single day to, I don't know, draft emails or write code. This deep dive is going to take you completely under the hood. We're revealing the hidden engine mechanics that are about to make those exact tools radically faster.
Right, and capable of remembering vastly more information, which is key. But to really appreciate the magnitude of this breakthrough, we have to start by clearly defining the two opposing forces that this paper connects.
Right, the architecture wars.
Exactly. So, for almost a decade, the AI industry has been ruled by a single monolithic architecture, the transformer.
The absolute reigning champion. I mean, if you're using a major AI tool right now, there's like a 99% chance it is running on a transformer.
Absolutely. And the defining mechanism that makes a transformer work is something called causal attention.
Causal attention.
Yeah. Essentially, when a transformer processes a sequence of text, it has to constantly look backward. It takes the current word it's looking at and mathematically compares it to every single word that came before it in the sequence, just to understand the context.
Okay, let's unpack that, because comparing words sounds simple until you scale it up. I like to think of a transformer as being basically like a massive dinner party.
Oh, that's a good analogy.
Right, like everyone at the table has to talk to everyone else simultaneously just to understand the flow of the conversation.
That is a great way to visualize the chaos. And that chaos points to the transformer's fatal flaw, which is quadratic scaling.
Quadratic scaling. Let's do the math on that dinner party.
Yeah, let's look at it. If you have 10 people at the table, that's 100 possible connections. But if you double the table to 20 people, you don't just double the connection.
Right, it goes way up.
You quadruple them to 400. So if you feed an AI 1,000 words, it makes 1,000,000 connections.
Wow.
And if you want to feed it a 100,000-word novel, you are suddenly asking the computer to calculate 10 billion connections for every single step of the process.
So the amount of compute time and memory doesn't just grow predictably, it completely explodes.
It explodes quadratically, exactly, during what we call autoregressive generation, which just means the AI is generating its answer one word at a time. The transformer requires a massive cache of working memory to hold all those past comparisons.
Right, it has to remember every single interaction at that dinner party.
Yes, so if you want an AI to read an entire code base instead of just a single Python script, the computational cost to power that memory cache becomes astronomical. I mean, it requires massive clusters of supercomputers drawing immense amounts of electricity.
Which perfectly brings us to the challenger in our source text, which are structured state space models, or SSMs.
Right, SSM.
And the most famous example recently is the Mamba architecture. Now, from reading the paper, the defining trait of an SSM is that it operates on linear scaling, right?
Exactly.
Linear scaling. It maintains a constant state, size, like a fixed amount of working memory, no matter how much text you feed it. So, if transformers are that chaotic, overwhelmingly loud dinner party, SSMs are more like a highly disciplined game of telephone.
I love that. A game of telephone where the message actually improves as it goes down the line.
Right.
An SSM processes one word, updates a running mathematical summary of the conversation, and then passes only that compact summary to the next step.
So it's not looking back at everyone.
No, not at all. It doesn't matter if you are on word 10 or word 10,000. The computational effort to process the next word remains exactly the same. The memory footprint never grows.
Okay, I have a major pushback here, though.
Go for it.
If SSMs are so much faster, and if they scale linearly without that massive quadratic explosion in memory and electricity, why hasn't the entire AI industry just thrown away transformers? Like, why are we still using them if this purely linear alternative exists?
That is the million-dollar question.
Yeah.
And it all comes down to the physical hardware and really the history of how computer chips have evolved over the last 10 years.
Okay.
Yeah. SSMs and transformers were developed in completely different academic silos. Because transformers have utterly dominated the market, the hardware industry, specifically companies building modern GPUs, spent billions of dollars building microchips optimized perfectly for the transformer-specific flavor of quadratic math.
Right, because GPUs are basically giant, incredibly fast calculators that only want to do one thing, which is multiply massive grids of numbers all at the exact same time.
Exactly. Parallel processing.
Parallel processing.
And transformers are built entirely on those parallel matrix multiplications. The chip manufacturers literally hardwired their silicon to do that specific math as fast as physically possible. They built, an intricate system of superhighways specifically designed for transformer cars.
And then the SSMs show up to use the highway.
And they find out they can't.
Oh, wow.
Yeah, because SSMs operate fundamentally differently. They rely on sequential recurrences. Think about your game of telephone person C cannot pass the message to person D until person B has finished talking to person C.
Right. It's one after the other.
You have to compute step A before you can compute step B. Because of this strictly sequential nature, SSMs could not take advantage of all those highly parallel hardware optimizations on modern GPUs.
So the GPU wants to do 10,000 math problems simultaneously, but the SSM forces it to do them one at a time.
Exactly. The physical chip ends up just sitting idle, waiting for the next step.
Yeah.
So theoretically, SSMs were vastly more efficient. But practically, on the actual microchips sitting in server farms today, they faced massive speed bottlenecks.
And that hardware incompatibility, that friction, is the exact spark for the massive discovery of this paper.
It really is.
Dow and Albert Ghosn didn't just try to code a slightly better SSM. They zoomed all the way out and mathematically proved that transformers and SSMs aren't actually opposing architectures at all.
Right. They introduced a unifying framework called Structured State-Space Duality, or SSD.
SSD?
Yeah. The authors dug deep into a well-studied class of mathematics involving what are called structured semi-separable matrices. And through that math, they discovered that the linear complexity SSMs and the quadratic complexity attention mechanisms of transformers are deeply fundamentally connected.
Here is where it gets incredibly fascinating. For you listening, imagine two factions of scientists spending years fiercely arguing over whether ice or steam is the superior technology for an engine. And then this paper drops on their desks and proves mathematically that they are both just H2O. They are the exact same substance. And depending on what your physical hardware needs in any given millisecond, you can seamlessly switch your data between the ice state and the steam state.
That's a perfect way to look at it. The duality proves that a single model can possess both the SSM-like linear efficiency and the attention-like parallel processing capability.
But, okay, I have to stop you there because my brain is breaking a little bit on the physics of that.
Good.
How can a mathematical function be quadratic, meaning it's comparing everything to everything simultaneously, and linear computing one step at a time at the exact same time? Like, how do you mathematically switch between those two states?
To understand how they switch, we have to look at a concept the paper relies heavily on called tensor contractions.
Tensor contractions.
Yes. A tensor is essentially just a multidimensional grid of numbers. Imagine a massive Rubik's Cube made entirely of data. The paper shows that both the SSM architecture and the transformer attention architecture are fundamentally just a massive four-way multiplication of these data grids.
Okay, so 4 grids of numbers being multiplied together.
Right. You are contracting or multiplying these huge grids together to get a final answer. The only difference between a transformer and an SSM is the order in which you group those multiplications.
Wait, really? Just the order?
Just the order.
Yeah.
Think back to basic algebra and the associative property. If you have to multiply A times B times C, you get the exact same final answer, whether you calculate A times B first or B times C first.
Oh, right. The final output doesn't change, but the intermediate steps look completely different.
Exactly.
Let me make sure I'm tracking this. If we group the massive grids of data one way and multiply those specific axes first.
You create a massive temporary matrix that pairwise compares every single token to every other token. You get the quadratic attention mechanism of a transformer.
But if we just group the exact same underlying grids of numbers a different way,
Then you keep the intermediate matrices small and compact at every step, creating the linear cumulative sum of an SSM.
that is wild.
The paper mathematically proves that if you set up the data grids correctly, the resulting models are exact duals of each other. They compute the exact same transformation of the sequence, just taking two completely different mathematical paths to get there.
I mean, that is beautiful theory. Finding the hidden associative property that unites the two biggest architectures in AI.
It really is elegant.
But, you know, theory doesn't draft my emails or analyze my spreadsheets. To make this breakthrough actually useful for the AI tools you and I use every day, this purely mathematical duality had to be translated into physical silicon.
Right, it had to be engineered.
It had to be built into a real-world engine. Which brings us to the creation of the Mamba-2 architecture.
Exactly. The SSD framework birthed Mamba-2. Because the authors could now treat the model as a unified mathematical structure, what they call a semi-separable matrix, they were able to invent a highly efficient block decomposition algorithm to run it on GPUs.
Block decomposition. Okay, help me visualize how this algorithm physically processes a massive amount of text.
Okay, so imagine you have a massive, complex textbook to read and summarize. A pure SSM approach would require you to read it word by word, sequentially, from page 1 to page 1000.
Which is highly memory efficient, but incredibly slow because you're doing it all alone.
Exactly. But with Mamba-2's block decomposition, you take that textbook and physically tear it apart into individual chapters. You hand those separate chapters to 10 different friends.
Okay, I have 10 friends reading 10 chapters simultaneously.
Because they're reading their own specific chapters in isolation, they can use that fast, parallel, quadratic attention. The GPU loves this.
Right. It gets to multiply huge grids of numbers simultaneously.
Yes. We call this the interchunk computation. But to make sure the book actually makes sense as a whole, once your friends finish their chapters, they don't read the whole book to each other.
So what do?
They just pass a tiny one-page summary, that linear state we talked about,
Yeah.
between each other to link the context of chapter 1 to chapter 2, and so on.
Oh, wow. So you are tricking the GPU into doing what it loves. Parallel quadratic math on the small bite-sized chapters, while the overall system still maintains the incredibly lightweight linear efficiency of an SSM.
That is the magic of the algorithm. The diagonal blocks of the math matrix handle your friends reading the individual chapters simultaneously, utilizing those specialized matrix multiplication units on the GPU, and then the off-diagonal blocks handle passing the summary state between them.
That perfectly solves the math computation. But there's another massive physical bottleneck when building world-class AI models.
Oh, definitely.
The original Mamba-1 struggled heavily with massive scaling across giant server farms. When you're training a model on 10,000 GPUs at once, you run into actual physical physics problems.
Heat power.
Yeah, heat, power, and mostly just the sheer time it takes to send data over a physical cable from one chip to another. How does Mamba-2 fix the communication bottlenecks?
This is a crucial part of the paper, these systems optimizations. Because Mamba-2 is built on this new duality framework, it can now utilize something called tensor parallelism.
Tensor parallelism.
Yes. It's a hardware optimization technique originally developed for massive transformers, heavily popularized by NVIDIA's Megatron system. It allows you to shard, or basically split, the model's brain across multiple different chips so they can share the workload.
And Mamba-1 couldn't do that.
Not efficiently. In Mamba-1, the parameters, the actual mathematical instructions that tell the AI how to transition from state A to state B, were produced sequentially.
Right, because of that telephone game.
Exactly.
Yeah.
They depended on the data that came just before them. So if you tried to split that process across 4 different GPUs, GPU number 2 would have to sit completely idle, waiting for a piece of data to travel over a cable from GPU number 1.
Yikes.
They would have to constantly pause and talk to each other to share the updated states. And in the world of supercomputing, waiting for data to cross a wire is an absolute eternity. It created massive latency.
So the GPUs spend more time talking to each other than actually doing the math. How does Mamba-2 bypass that waiting game?
Mamba-2 completely redesigns the neural network block. It takes all those key parameters, the instructions for the math, and produces them in parallel at the very beginning of the sequence, before any of the sequential mixing even happens.
So it hands out the instruction manuals to all the GPUs before the timer even starts.
Exactly. By doing this, it cuts the required GPU synchronization points in half. The GPUs can grab their instructions, compute their portions independently at top speed, and only need to sync up over those physical cables once at the very end of the layer. This allows it to scale across thousands of chips just as efficiently as a transformer.
The paper also dives into something called sequence parallelism as another hardware fix. What problem does that solve?
It solves the problem of processing incredibly long documents that literally cannot fit onto the memory chips of a single device. Mamba-2 can chop a massive sequence up and pass the hidden state seamlessly between devices. But even more practically, it inherently handles variable sequence lengths without needing something called padding tokens.
Padding token, I've seen that term before. That's when you feed an AI a short email and a long essay at the same time, right?
Yes, exactly.
Yeah.
In traditional transformers, the parallel math requires everything to be exactly the same shape. So if you process a 10-word email and a 1,000-word essay in the same batch, you have to add 990 invisible blank padding tokens to the email just to make the grids of numbers line up perfectly.
Right, so the shapes match, but the GPU still has to do the math on those 990 blank tokens, doesn't it?
It does, which is a massive waste of electricity and compute time.
It's literally doing millions of calculations on empty space.
Mamba-2 eliminates that entirely. Because of how the state space math works, Mamba-2 can just set a single parameter to 0 at the document boundary. It creates a mathematical wall that prevents information from bleeding over from one document to the next.
Well, that's clever.
Meaning you never have to pad short documents again. The compute efficiency just skyrockets.
Okay, so the theory is beautiful, and they've completely redesigned the architecture to perfectly exploit the physical reality of modern GPU hardware. But the ultimate test of any engine is turning the key and taking it to the track. What happens when they actually benchmark Mamba-2 against the best models in the world?
The empirical validations in the paper are incredibly strong. First, just looking at raw mechanical speed, the new SSD implementation is anywhere from 2 to 8 times faster than Mamba-1's optimized scanner.
2 to 8 times faster. That's a massive leap.
It is. But what's truly revolutionary is that it achieves this speed while allowing for a massively larger recurrent state size.
Explain what the state size practically means for the model, just to be clear.
Sure. State size is the capacity of the model's working memory, the size of that running summary it passes down the line. Mamba-1 typically had a state size of 16. Mamba-2 can easily run at a state size of 64 or even 256 without any significant slowdown.
Wow. To put that in perspective, going from 16 to 256 is like upgrading from an AI that can barely remember the context of a single paragraph to an AI that can keep an entire coding manual active in its working memory while it writes a program for you.
Exactly. It can hold on to vastly more context. And that larger capacity shows up directly in the language modeling test scores.
How did it do on the tests?
Well, the authors tested Mamba-2 against the chinchilla scaling laws, which is basically the industry standard for measuring model efficiency. They trained models of various sizes on 300 billion tokens of data from the Pile dataset.
Okay.
A 2.7 billion parameter Mamba-2 model thoroughly outperformed the previous Mamba 2.8b model. But remarkably, it also outperformed the much larger Pythia 6.9b transformer model on standard downstream evaluations.
So it beats the competition on sheer speed, efficiency, and the final test scores.
Across the board, yes.
Now, I do have to ask about a specific weakness. One of the most common complaints I hear about linear models, like early SSMs or old recurrent neural networks, is that they suffer from amnesia.
Yes, the forgetting problem.
Right. If you have a constant state size, even a large one of 256, eventually old information gets overwritten by new information. It's like trying to find a specific name in a massive phone book that you only glanced at an hour ago. The exact data point gets lost in the running summary. So how does Mamba-2 handle deep, specific memorization?
You are hitting on the exact historical weakness of these architectures. And the paper explicitly tests this using a benchmark called the Multi-Query Associative Recall Task, or MQAR.
MQAR, okay.
And the authors literally describe this in the text as a phone book lookup task. The model is fed a massive list of key-value pairs-like names and phone numbers, and later prompted to produce the correct number when shown a specific name.
The ultimate stress test for an AI's memory.
Exactly. Mamba-1 failed heavily at this task as the sequence got longer. The information just washed away. But Mamba-2 absolutely crushes it. In fact, it matches the performance of a pure vanilla transformer attention model.
Wait, how is that possible if it's still compressing the data into a summary?
Because the SSD layer leverages the GPU's matrix multiplication unit so perfectly, it can afford to maintain that massive state size of 256 we discussed earlier. That larger state acts like a vastly larger internal notepad, allowing the mathematical summary to retain high-fidelity details of far more key-value pairs without dropping them.
That is incredible. A linear model that doesn't forget.
Yeah.
But I know the paper doesn't just end with a victory lap for pure Mamba-2. There is a surprising twist at the very end regarding the absolute best performing model they built.
There is, and it brings the entire concept of the deep duality full circle. After proving that transformers and SSMs are mathematically the same and building an engine that can do both, the researchers found that the absolute best performing model isn't purely Mamba-2. And it isn't purely a transformer either. It is a hybrid of the two.
A hybrid, so they are actually mixing the physical layers within the neural network.
Exactly. They experimented with different ratios and found that a mix of about 10% attention layers and 90% SSD layers hits the ultimate architectural sweet spot.
That's so specific. Why does that specific ratio work so well?
It comes down to specialization. The 90% SSM layers act as a highly efficient, incredibly fast general sequence mapper.
Right, doing the bulk of the reading.
Yeah, they process the vast majority of the context linearly, summarizing the flow of the document without burning through massive amounts of memory. Meanwhile, those two 10% attention layers act as a razor-sharp retrieval mechanism.
Oh, I see.
Right, so if the model needs to quickly and precisely look back at one highly specific token from 50 pages ago, the attention layer handles it perfectly, without forcing the SSM layers to try and compress every single granular detail into their working memory.
Wow. So to bring this all together for you listening, Tridao and Albert Gu didn't just iterate on an existing design to shave off a few milliseconds of compute time. Through the brilliant mathematical bridge of structured state-space duality, they have proven that the two biggest warring factions in AI architecture are actually just two sides of the exact same mathematical coin.
Beautifully said.
They took the linear, lightweight speed of SSMs and united it with the hardware-friendly matrix multiplication power of transformers.
And by building the Mamba-2 architecture on top of that duality, they have created an engine that can scale massively across modern GPU clusters without those nasty communication bottlenecks. It processes massive sequences of data 2 to 8 times faster, expands its working memory exponentially, and matches the deep pinpoint memorization capabilities of pure attention.
Which means, practically speaking, the AI tools you rely on every day are about to cross a massive threshold. Soon, you won't just be feeding an AI a few paragraphs or a single PDF. You will be able to feed it entire libraries of books, massive enterprise code bases, or hours of raw audio, and it will process all of it incredibly fast.
Exactly.
And crucially, it won't require massive, prohibitively expensive supercomputers drawing the power of a small city to run it. It is a fundamental, ground-up upgrade to the engine of artificial intelligence.
It really is a remarkable engineering feat. But to me, the duality framework raises an even more profound question, something for you to consider long after we wrap up this discussion.
Oh, I love a good philosophical curveball. Let's hear it.
If we have just proven mathematically that two completely different ways of processing information, like the continuous linear summary-based memory of SSMs and the simultaneous hyper-focused pairwise connection of attention, if those are actually just two different perspectives of the exact same underlying mathematical matrix, what does that say about human cognition?
Oh, wow.
Think about it. Are our own seemingly distinct mental processes, like our slow, continuous long-term memory that summarizes our lives, versus our immediate, hyper-focused attention on a specific detail right in front of us, are those really different biological systems? Or are they just different tensor contractions of the exact same neural algorithm inside our brains, just waiting to be mathematically unified?
That is an incredibly profound thought to leave on. The next time you open up an AI to write a quick email, just remember the incredibly elegant physics operating silently under the hood and how closely they might mirror the brain actually writing the prompt. Thank you for joining us on this deep dive into the architecture of intelligence, and as always, stay insanely curious.